sort of introducing this topic, Network Digital Earth, I thought of something when I came up with this acronym. Whatever I thought of initially, I've been happy to see that there's a lot more that I learned over the course of this one day and could, which is 2 more days, so 3 days of this talk. So I'll try to first of all though tell you a little bit of what I was thinking initially when sort of this Network Digital Earth idea, a few of us were discussing back and forth. So I'll talk about what I'm calling somewhat grandly general principles. It's not really principles, it's just what people have talked about and why we could think of digital earth and something that's network, and then I'll give you one specific example. So there's a lot to cover. I may rush a little bit. Please feel free to raise your hand and stop me and ask me questions anytime. By the way, in general, if after this or at any point in time I avoid you or I seem to run away, it's not because I'm running away from your questions or I don't like you, but I don't want you to catch this vital thing that I have, which is decreasing now for me, but this is the time when I think I'll pass it on to you. Anyway, so first of all, here are all the funders. So I'd like to acknowledge all of them: NSF, NASA, Department of Defense, Energy, Homeland Security, etc., over in the US. And I have 2 hats now. So I'm at Northeastern University and I'm at a spin out that a former PhD student has started, that's called RISC. So with those acknowledgements out of the way, what is this concept of digital earth? So some of you may or may not believe that Al Gore invented the internet. How many of you have heard this thing, that Al Gore invented the internet? Some of you have. Well, whatever our belief in that, it is true that he did invent this concept of digital earth, and it is very visionary. I think, by the way, Al Gore is wrongly blamed for claiming that he never really said he invented the internet as such. But anyway, that is another point. But he did give this concept of digital earth. So his idea was that there is all the information that we have about planet Earth now, historically, and in the future. You give all of this information in a visual, user-friendly way, which a 10-year-old child should be able to look around and get his or her questions answered. So roughly of that order, that kind of thing. So he said we have an unparalleled opportunity, and digital earth is multi-resolution, 3-dimensional representation of the planet into which we embed vast quantities of georeference data set. And then he talked about some potential applications. This was 1998, and he was already talking about virtual diplomacy, fighting crime, preserving biodiversity, predicting climate change, increasing agricultural productivity. So I am, of course, a bit biased towards Al Gore since I work in climate change. He came to one of our conferences, American Geophysical Union, and said, I am forever your possible president of the US. Almost there, but never happened. Would have been great though. See, a kind of vision like this. So anyway, going from this vision, the question is Google Earth, just as an example, is that a realization of this digital earth vision? So some of you may have heard about Michael Goodchild. He is one of the gurus of GI science, as it's called. So he and his colleagues came up with this paper in this Perspectives article in Proceedings of National Academy of Sciences, which was actually called Next Generation Digital Earth. So I have some of this text here, which it's okay if you don't read all of them, but he said that the era of big data has arrived. The general public is getting more and more engaged. Google Earth has stimulated some progress, but is there more that needs to be done? And here are the 3 things that the article said. He says that the current generation of, if you call these virtual globes, they sort of fall short of Al Gore's vision in three areas. First of all, in terms of historical exploration or forward simulation capabilities. So we can see what is happening right now, but if we have to go back and say, and one example I think they gave is, okay, we are sitting here now, and this is near the Hijli jail. So if you want to get an understanding of what was happening here 50 years, 100 years back, maybe there was this Indian freedom fighter who was trying to escape, and surrounded by British soldiers. Well, that may be too much to understand, but at least what was happening in this place in terms of land use, climate, vegetation, that kind of thing, we might want to know that, and that's not the capability that we get yet. Similarly, if you are trying to look in the future, what will sea level rise, climate change, other kinds of things, population change, what will this mean, or what could this mean for this place eventually? So that's one thing. The second thing is, not all data are treated equal. So the point that they made is, even the way that Google acquires these data sets and the kind of terms of use that they impose, and the strategies that they have, and even if it's not just Google Earth, there are other kinds of things, different virtual globes. NASA has something called Whirlwind, I believe, and then these geo portals. They have various capabilities, but don't quite reach that level where you have all these data sets. Excuse me. And the third thing is, all these systems have difficulty communicating information that's not inherently visual. So whether it's about biodiversity, whether it's something else, one thing, and these are all quotes by the way, one thing that I particularly was interested here is, uncertainty is even more problematic, as there are no obviously intuitive ways of conveying the magnitude or implications. We are used to seeing a single solid world rather than a world of conflicting possibilities. And I'll show you that example in climate, where you'll see that we have to deal with plausible futures in terms of the kind of things that may happen. We cannot just think of, here is this one single prediction. Even this place called Wall Street, and many of my students are attracted by these finance kind of things, so I have a little bit of negative feeling about those, but even those people don't go just with predictions these days. They care more about the variability, they care more about risk and uncertainty rather than predictions. And when we are dealing with some of the more complex entities such as climate change and such, we have to think about those. We cannot think about one single point prediction, we think about a world of plausible futures. So that's very important. All of these things, of course, are important. So this is in terms of next generation digital Earth. Here are three pictures that they have in this paper as illustrations. The first picture, if you, this is again from their paper. So they are saying that, just as an example, if you know that there are all these underground pipes and things like that here, can you just turn on a feature which will let you see the landscape as it is, and also let you visualize underground what kind of, let's say, water pipelines, other kind of cables that you might have. Similarly, in terms of different models, they are saying that, can you visualize models of the built system, buildings, how some earthquake strikes, how they'll behave in the future with sea level rise, how much of those will be impacted, etc., etc., models of these systems. And they're showing some examples of, even today, some visual representations that we have, such as they're giving this example of the map of India, and as they're saying, if the query to Google Earth, let's say, comes from the government of US versus government of China versus government of India, they come up with three different maps, right? So that's interesting in terms of what you have to do, and this is just an example, by the way. So that's in terms of digital Earth, where it started and where we are right now. Now let's get to network risks. So this is a paper that came, again a perspectives paper that came in Nature. This was 2013 by Helbing, which shows all kind of risks that you might imagine in what he calls the globally networked Earth. So starting from economic disparity, climate change, slowing Chinese economy, all kinds of things, and within that there was the food, energy, water nexus, different kinds of things integrated, and you have earthquakes, you have storms and cyclones, all kinds of things in here, and how these entities are connected right now. And as I was probably saying yesterday also, when we think of connections, there's a reason why these connections are imposed. I mean, it's not that we always explicitly build connections, but we don't stop them because they help each other. These connections help each other. However, they also mean that there are vulnerabilities. Some one thing fails somewhere, and that failure quickly spreads. So we have to stop that risk from happening. So here is the World Economic Forum report. I think borrowed from that. I'm sorry if this is not clearly visible, but I think whatever is visible conveys the picture. The World Economic Forum, the Global Risk Report, this is the 2018 report where some of you may have contributed. I think this person from World Bank may have contributed, I don't know. So they talk about the global risks interconnection map and the risks trends interconnection map, right? So things where, so this one on the left is very similar to that Helbing article where they're saying there are so many different things that are now interconnected, and the other one is where these risks, different kinds of risk, climate change being one of them, is pulling this entity. So one of our visions original visions, and again this has gotten modified just with this one day and one lecture that we have heard so far, and it's the best thing is when you think of something which is half-baked, I have now learned is to organize a conference with Niloy and Kuds, and everything gets much more sorted out with all your help, of course. But initially the idea was that this is a network digital Earth where we have the digital Earth concept, as I was explaining earlier. We have network science, which is, network science is sometimes defined relatively narrowly, as in certain, centrality measures, Barabashi, and all of that's relevant, but there is more to networks than network science of that order. There is graph theory, there is network optimization. So here we are including all of that, and what is being called big data science, and climate is a big data thing. So all of these things and then combined into what we call this network digital Earth, which will have this network science and engineering. Some things that we hear in network science is not always translatable to engineering solutions. Well, we want to think of all of those things together. An approach which has a hybrid physics data decision approach for targeting rare events. Sometimes rare events have disproportionate effects, rare or extreme or anomalies, and we want to address those, and then translating these to decision sciences, and then we want to target some key applications. So that was the original idea, and we had some key applications such as coastal ecology, urban lifeline, cyber security, ecological outbreak. Many of these we have heard today from this audience. So now coming to the networked digital Earth for climate change impacts specifically. I was talking about this yesterday again. So this is just a 3-level visualization, and some folks in our lab, especially Udit, who is here, came up with this, which is, that when we think about, if we think about climate and weather extremes as stressors, so then we have the climate networks as one representation of climate. Of course, is not the only representation. So let's say climate networks, big data, etc. And then we have the stressed system, which are the interdependent lifelines, which are things like transportation networks, communication networks, power grids, water distribution systems, wastewater systems, and ecological networks. So if we are expressing all of these as networks, again, network is not just this one medicine, this silver bullet that solves everything. That's just the idea is that there are descriptions that we could characterize through networks in many of these systems. These systems are interlinked, and in that sense at least, many of these automatically get classified into networks, and in some of these, if we categorize them through networks, then the topology of those networks help us get some insights. But there are other things we also need to do. And similarly, in the area of social networks, starting all the way from social networks within social media helping in emergency response, all the way to things like finance, where some crash somewhere cascades all across the world, etc. Social networks is one area where we haven't, meaning my group hasn't done much work, but we have already heard a lot of talks in that area here. These two areas we have been doing some work. This Wikipedia article on climate as complex networks, I just wanted to mention it. Again, this is something that I believe Udit and Shashank, both of whom are here, did, or at least initiated as part of a course that they took with Professor Laszlo Barabashi, right? Please feel free to correct me. And now, of course, it has gotten edited, so you can see what that is. Anyway, so and the other thing is that all of these uncertainties, all of these projections, these plausible worlds, we would like to translate to risk assessment, to something based on which decisions can be taken. So here is one example. This comes from IPCC, the Intergovernmental Panel on Climate Change. They have a risk framework which talks about the following. There is a risk assessment. By the way, many of you may know that today when in insurance, or when natural hazard strikes, including weather extremes, it's called an act of God. Do you know that? It's called act of God. And irrespective of our belief in God or not, right, that's independent. But I think most of you will agree when I say that she is unfairly blamed these days. Because first of all, if you think of weather extremes, even that is not totally, humans are not totally free. They cannot, we cannot just say it's God. We contribute to the weather extremes per se. But in addition to that, for a hazard to turn into a disaster, some other things need to happen. It's not just the cyclone in Odisha, but there were infrastructures that were not ready. There were remote sensing, early warning capabilities that were not ready. There were people living in vulnerable places. So it's the vulnerability and exposure that adds on to the hazard to turn a hazard into a disaster. So again, whether it's the hazard itself, especially if it's a weather extreme, or whether it's turning the hazard into a disaster, God is often unfairly blamed. But the thing is, then, first of all, we need to assess that the risk of that hazard, and that includes the hazard itself, vulnerability, exposure, and to think probabilistically. It's, let's say, probability of a cyclone in Odisha given climate change, climate variability, including global, regional climate, and then probability of damage given that cyclone. So that would typically imply infrastructural strengths, and then exposure of people and assets in the path of that cyclone. So, but once you have done that, then the other things that are of interest is how do you manage consequences. Despite your best efforts, some disasters will happen, and you need to be able to manage those consequences, including pre-disaster, preparedness, during disaster emergency response, and post-disaster recovery. So that's that time frame. And then in the longer time frame, there is a need for adaptation plans, what you do in advance to get ready. And then in even longer time frame, if you will, or similar time frame, there is a need for mitigation. Difference between adaptation and mitigation is we are sort of managing the unavoidable. Some things will happen despite your best efforts. You need to plan for things in advance so that they don't get too bad. So it's managing the unavoidable. Mitigation is avoiding the unmanageable. So it's, we are trying to then reduce greenhouse gases, trying to reduce the renewable energy, all those kind of things, so that the worst things don't happen. So that's what the IPCC says in terms of hazards. Some of those concepts can then be translated to, and we have done that, others have done that. This is our work for the town of Brookline, which is a small town in Greater Boston region. Unlike in India, where, for example, everybody wants to say, I'm from Calcutta, and I did my +2 from Narendrapur, where we are very happy to say Narendrapur, but now, they say, no, we are from Calcutta. Everybody has to be Calcutta. There is exactly the reverse. Nobody wants to say, I am from Boston. Oh, yeah, okay, there's a small place near Boston. Either I am Cambridge, or I am Brookline, or I am this and that, and everybody wants to have their own climate action plan. So it's the town of Brookline. We have done some work with the city of Boston. Town of Brookline called us to understand public health impacts of heat waves. And then this kind of framework could be modified for urban heat waves in the context of public health impact. The US Department of Energy's ARPA-E is one of the advanced research wing of the US Department of Energy. So they called us to understand water energy nexus, specifically risks of power production because of water scarcity and warmer stream temperatures. And again, we could formulate that problem in risk framework using ideas from here, conceptually similar to this, and then try to do something there. So this kind of framework is fairly generalizable, but the idea is we have to start translating the information that we get into things that are usable, to help generate risk-informed decisions and policy, and ultimately into resilience. So by that we mean that it's not just the immediate response that counts, but it's also how well we recover. And people have been talking, there could be suboptimal recovery, that town or that city or that place never really fully recovers, all the way to a recovery where you actually learn from the hazard and try to get better, so that next time you are a little bit better off. And these kind of things conceptually had been characterized before. What we tried to do in the context of lifeline infrastructures such as Indian Railway Network and US Airways, and now we are trying to do that for ecological systems. Shashank showed one example of that, and also for one city, so city of Boston, we are looking at power grids and subway system, how to look at how that system might fail and what is the best way to recover. All right, so that's an overview, and by the way, we had done some then similar studies or proposed similar work in the context of climate change impact on cities together with our colleagues. All right, so now let me come to a case study which I'll try to cover quickly. How much time do I have? Yeah. So which talks very specifically about one aspect of climate change, and which I have just actually borrowed from a previous talk that I had that I gave at International Conference on Data Mining. There is a spatial and spatiotemporal data mining workshop, so I was asked to give a keynote there, so I'll talk about that. So the keynote was titled Spatiotemporal Chaos as I called it the next generation grand challenge in machine learning. I called it the because it was a spatiotemporal data mining conference. It's probably one of the many. So this also serves as an illustration of some of what I was saying earlier. So spatiotemporal chaos. How many of you have heard about chaos in the context of either space-time or chaos in the context of chaos theory? Not the chaos that you get in school when the teacher leaves, but something else. Some of you have heard about. Okay. So chaos is, think turbulence. When you go by airplane, suddenly you hit air pockets. Even think hurricanes, cyclones, things of that nature, right? Chaos has some specific mathematical definitions. I'll come to that in a minute. But I was just trying to illustrate this. This is a painting by Van Gogh. How many of you have heard of Van Gogh? Good. If not chaos, at least Van Gogh. Same thing, by the way. So he's supposed to have cut off his ear or something, right? That's how the story goes. But here is a painting It's a fairly famous painting. It's called The Starry Night. The night sky is depicted by Van Gogh. And some of the words I sort of emphasized is, this is surreal and stylized. And many feel that Van Gogh's turbulent quest to overcome his illness is reflected here. Turbulence and some of these, surreal, maybe even stylized, even some of these shapes that you see here, these roundish shapes, many of these are hallmarks of chaos. I'll tell you why. All right. So, little bit mathematical first. Many of you know about, in the constant velocity equation dx dt equals v, right? If you solve that equation, what do you get? There are some students here, right, who still do hands-on work, I hope. If you solve dx dt equals v, what do you get? A curved line, linear, parabola, straight line. V is constant. Okay, think about it. So I also have a drawing there about what you get. So if dx dt equals v is constant, then you have a straight line, right? It'll go up like this. It's like y equals mx plus c kind of equation. Okay, so it's okay, and then so that's one thing. Now, how many of you have heard of a thing called white noise? Okay, some of you. How many of you have heard of Gaussian distribution, bell-shaped curve, normal distribution? All of you. So white noise is just a process where at any point in time t, let's say I'm coming up with a time series y. So at any point in time t, yt equals epsilon t, where epsilon is drawn from a bell-shaped normal distribution, Gaussian distribution. So I have two things here, dx dt equals v. By now have you solved that? Is it a straight line to all of you now? X equals x0 plus vt, right? Y equals y ax plus b. So a straight line. And then white noise. Why is it called white noise? Because it's, think of it related to a spectrum of light. White noise, if you just draw from a distribution, it's sort of, if you plot it in frequency space, it has contributions, equal contributions from the entire spectrum, theoretically. That's why it's called white noise. Okay, so these are simplest things. If you take that time series created out of white noise, and if you have enough number of those, plot a histogram, you should get a bell-shaped distribution. It's IID, independent and analytically distributed. Nothing really interesting about it, nothing much. Okay, and similarly dx dt equals v, it's a straight line, nothing much, not much interest. Now make these a little bit complicated, just a little bit complicated. So yt equals epsilon t, right? Make it a little bit more complicated and say yt equals yt minus 1 plus epsilon t. Okay, so yt equals epsilon t. Think of it. If yt is the wealth, right, and epsilon t is the amount of money that you get at each point in time. So let's say you go to a casino and you toss a coin or do something and you get epsilon t. So at any point in time, each of that person has epsilon t wealth. And if you are following random walk, then at each point in time, you are giving up that wealth, you are getting something else. So it may be some wealth that you get, or you may even get some debt. It could be negative also, right? So you have some wealth or have some debt, and then next point in time you sort of forget all about that. Whatever debt you had, etc., you again start from scratch and you get another set of things. So it's very instant gratification, no long-term planning as such. Well, that's one kind of world. We don't live in that world. If we think of the next one, which is yt equals yt minus 1 plus epsilon, then you have your wealth or your debt accumulated from the last time step and you get something else now, epsilon t, right? So yt equals yt minus 1, whatever you had earlier, and then something else which is random, and you continue like that. The interesting thing is, if you continue like that, right, this is just a random thing. I have whatever wealth I have and I get something in random. So if two of us have the same kind of strategy, this is my strategy, and let's say one of those is Professor Ravi Sundaram and one of those is me, right? What happens is, just by random, because of random reasons, Professor Sundaram will go here. So his wealth has really gone up, right? And he has played his life in the same way, randomly. But all of you will go to him and say, Professor, what's the secret of your success? Can you write a book about it? And meanwhile, what happens to me is, I am here and I am a miserable failure, right? But all of it is random. But think about it, something as simple as that gives rise to all kind of profound behavior. Rich person, poor person, global warming, global cooling, you take it, right? Something as simple as that. Now, on the deterministic side of things, dx dt equals v, make it slightly more complex. It's not that much more complex. I have, instead of one state variable, I have three state variables now, x, y, z, dx dt, dy dt, dz dt. Sigma, rho and beta are constants. I have simultaneous ordinary differential equation. This is called the Lorentz equation. This is a chaotic equation. This is extremely sensitive to initial conditions, and in what is called the phase space, so if you plot x versus y, y versus z, etc., you get this butterfly effect. You get this thing that looks like a butterfly. Lorentz called this butterfly effect for two reasons. One is you actually get this kind of shape in the phase space. It's called a strange attractor. But the other reason is that, you know, these are extremely sensitive to initial conditions. So he said the flap of butterfly's wings somewhere in Brazil might cause a hurricane in North America, etc., etc. But these have real implications for us. Even now we sometimes see, okay, all these weather models are predicting that the hurricane will most probably hit Tampa, which is on the west coast of Florida, or will hit Miami, which is the east coast of Florida, but it hits the west coast of Florida instead. Even now we have those kind of things, right? And these are the reasons there are some bounds on what we can do with these kind of things, okay? So it's not just the large data that bothers us in climate, and data is large, but it's also the complexity of the data. And this is just an example of two different types of complexity, stochastic and deterministic. And what we have in climate is this fifth thing, which is a combination of both of them. Spatiotemporal chaos, by the way, is pervasive in fluid dynamical systems. As I was saying, you know, turbulence that we encounter in airplanes, entry to Mars. I've been working with some colleagues at NASA, and they have been trying to entrain me into this. I don't know what it means just yet, but they are actually trying to find out some of these things to determine landing patterns in Mars. And I think at some point India will follow too, right? Given the kind of strides ISRO has been making. Hurricanes themselves, these can be thought of as eddies in the climate system, turbulence. And things like wind stress. So one of our work in wind stress and what is called upwelling, how that's changing with climate, we have done some work there. So all of these kind of things relate to spatiotemporal chaos, which, by the way, this uncertainty, this chaos, this extreme sensitivity to initial conditions is exacerbated by how connected things are. And I think Udit will talk a little bit more about that. So I'll just quickly mention here that in India, in 2012, delayed monsoon and heat waves gave rise to some surge in agricultural water demand, partly because of the incentives that was there in terms of drawing groundwater, which led to increased stress on the power grid, which in turn caused the 2012 India blackout, which had then impacts on Indian railway system, which quickly spread across the railway system, right? So again, Udit will talk more about that. I don't want to steal the thunder here, but just an example of how things can quickly cascade from built natural human systems. Okay. Some of the work we have done in climate, and here's this example of big data in climate. So we have, this is a projection of how quickly climate data is supposed to grow. This comes from this paper in Science. So they are saying this orange thing is archived model simulations. Climate models are complex, so you don't discard their runs when you have them. They are stored as data. So that's the orange one. And then this is the satellite remote sensing. And in situ is also increasing, in situ sensor data, but it's not visible in this graph that much, right? By the way, right now we are thinking this 350 petabytes. In 2030, that's a lower bound, because we'll have more model runs from initial condition ensembles, and I'll tell you what that means. One other thing that many things that we have to do with these kind of data sets. But one other interesting thing is sometimes in climate we have to generate even more data than we have. So climate models are low resolution, and what we have to do to be able to inform infrastructure or water resources or other kinds of decisions like that is sometimes downscale these models. And downscaling is one area where the physics, we understand some, we don't understand much, not as much as we'd like to in terms of climate downscaling at the scale, at the lead times that we are talking about. Anyway, we do statistical downscaling often. That's one of the techniques that used in addition to dynamical downscaling, which has some pros and cons. But if we are doing statistical downscaling anyway, then we might as well try other kinds of newer methods. So whatever Ravi might say about deep learning, maybe deep learning will work here. So we used single image super resolution here. That's one of my students, TJ Vandaler. It seemed to work well. So the idea here was to translate this this downscaling problem into one of image resolution problem. It seemed to work well. But the idea is that there is already a lot of data, and sometimes you might have to create more data set. Anyway, so in terms of physics, mathematics, machine learning, we cannot afford to stay in our whatever disciplinary background we have. If we have to solve this problem, we can say that we are happy where we are and we already do good things. I'm sure all of us do. But if we have to solve these problems, we have to get beyond some of our disciplinary thinking. There's already, in terms of methods, many of these things that are motivated already that we have to do. In terms of problems we solve, again, this comes from World Economic Forum report. This is the earlier one. I just didn't update my slides, but it sort of has remained the same. This is the likelihood of events happening. This is the impacts if events happen. And look at the very top, which is the highest risk. We have extreme weather events. And then we have water crisis, natural disasters, climate change, etc., all over here. So a lot of these risks are related to climate and water. And it's not just the World Economic Forum, it's the US National Academy of Engineering, it's the USAID, which emphasizes, of course, these things. So with that background on chaos and extreme sensitivity to initial conditions and stochastic variability, and if you'd call it chaotic or nonlinear dynamical variability, here is how climate change looks like, by the way. So if you think about the variability in climate, this is not something I created, this comes from IPCC, Intergovernmental Panel on Climate Change. So here the green band, first of all, here is where forecast started. This is historical, but even when you reconstruct history, you have some uncertainty. But over here, the green band is emissions. So how much emissions we might have in the future. That's, of course, nobody can exactly predict that. We don't even call that prediction, we call it projection. We treat those as what if scenarios. What if this was, because these deals with things like social change, population change, technological things that may happen in the future, all kinds of things like that, which are not predictable as such. Right? So more what ifs, what if this were to happen, that would happen. So that's why you have this range, this large variability. That's the green, that's understandable. Now the blue one is model spread. So this is different models of climate. So there are about 20 to 30 modeling groups across the world. They have their own models. The basic science is the same there. So think about the science as in, let's say, F equals ma. Most of you have heard about that equation before, right? So force equals mass times acceleration. That science is the same. But when you try to parameterize things like friction, F equals kma, that is sometimes not the same, and models do these things differently, and that's the kind of thing that, that's the spread that's caused by, that's represented in blue here. The orange thing here is internal variability. Orange thing here is intrinsic climate variability. That's the thing that you have with, that's analogous to chaos. That's the extreme sensitivity to initial conditions. So this part is irreducible uncertainty. If your physics improves, if our understanding improves, this blue part may gradually decrease. But this orange part is not going to decrease. And think about this, in the time frame where we have to make decisions, typically we don't make decisions 100 years later. We make decisions from now till 30 years. In that time frame, it's called near term in climate. not only is the trend comparable to the variability, but also the variability itself is dominated by the irreducible component of the uncertainty. That doesn't mean that we get overwhelmed by the uncertainty and we don't make decisions. That just means we have to be careful about that, not minimize the uncertainty and make decisions appropriately. So I'll skip some slides, but just to give you an example of how these things look. These are three different models. This is of course map of the US. These are three different models. Ignore the marginals for now. Three models, all US based models. The NCAR model, National Center for Atmospheric Research, NASA model and NOAA model. So all US based models, and these are two initial conditions. Look at these, the models differ from each other a lot, and this is, by the way, one of the hardest things. Just to give a little bit of context here, this is P minus E, precipitation minus evaporation, 10-year average and difference over 30 years. So if you looked at temperature, things would be much better. If you looked at temperature over 100 years later, things would be even more better. But here we are looking at things that are hard to predict but are very important. So P minus E, if you think of agriculture, that kind of thing is very important. So look at how much the models themselves vary, and initial condition, which is the irreducible part of the uncertainty, you would at least hope that one model would give one result and initial conditions would be clustered around that. No. So you have this range of behavior. And these things on the marginals are averages. So this is the average of all these models across one initial condition. This is the average of all these initial conditions across model 1, etc. This is the average of the average. Many times people said that we should make decisions based on the average of the average. Well, in this case, the average of the average says not much is changing. I mean, things are changing, but relatively speaking, not much is changing. Can we make decisions based on that? Well, that is like saying that if I say in the future 100 people will die because of floods and 100 people will die because of droughts, 100 minus 100 equals 0, so nobody is dying, we don't need to make any changes. If you are comfortable living with that, then yes, we can live with the average. Otherwise, what we have to do is we have to live with the variability. Some of this is reducible, some of this is not. We have to learn to live with it. The good thing is, some of us, engineers, mechanical, civil, electrical, we live with this uncertainty all the time. Even when we build buildings, bridges, we don't say that at each point in time, if the design life of my bridge is 50 years, at each point in time you need to give me exact prediction of how much traffic there is. We deal with statistics of traffic, extremes of traffic, peak traffic, and based on that we get a design load and we build on that. Here that design load has to consider both sides of the story, both sides of the uncertainty. And of course then that has to balance with the other considerations. This uncertainty, by the way, can be transformed into risk. So we have used exactly that uncertainty. We considered 350 ensembles from climate models, and we considered that in the context of water energy nexus. This was for ARPA-E. We considered things like changes, water stress coming from both rising stream temperatures and net water availability. So water scarcity and rising stream temperatures, because both of them are important for power production at risk. We considered exposure and vulnerability, and for water stress we considered climate change, multi-sector water demand, population change, and then we said, okay, here is the total water stress and here is how much power production at risk we might expect. 0 to 30-year time frame when climate is that much uncertain, but you still have to predict. What we can say is, of course, not everything agrees, but if you look at a graph like this, this is net water availability. So on the left is water scarcity. This is stream temperature. As you go up, you have warmer water. So this is scarcer, warmer quadrant. You see a tendency to move up there. And that's the kind of thing that you can get. That's the kind of uncertainty with which you have to make decisions. And one part of that work we also published in scientific reports, which goes a little bit into more detail of that. So thank you very much.
Hello. Thank you for the wonderful talk. So, if you could go back to the uncertainty slide with the blue and the orange curves that you showed, the one before that, this one. So, is this like, would you consider this to be like an uncertainty curve?
uncertainty, yes.
And so,
yes, go ahead.
if there is uncertainty, then you look at the green, the range that's represented by the green and the range that's represented by the blue. Would you say there are two different types of uncertainty represented by different colors?
Yeah. So the green one is like what if scenario. This is the uncertainty that comes as a forcing. Forcing meaning changes in emissions. So when you have emissions get into the atmosphere and cause changes in what is called radiation budget. So more of sun's energy comes in as shortwave radiation, but when the earth heats up, it goes up as long wave radiation. Some of that is trapped by these greenhouse gases and other things that are caused by these greenhouse gases. So this is talking about these greenhouse gases themselves. How much carbon dioxide will you emit? That gets into technological issues, renewable energy use, adoption, all those kind of things. These are almost treated as what if scenarios. The reason why I said it's still uncertainty is because if I'm making a plan in my city or in my water resources or whatever it is that I'm making a plan for, I have no control over that. So in that sense it's uncertainty, but still I know that some things are probably more likely to happen than others. The blue one is the uncertainty because of my lack of understanding of the physics. The full lack of understanding of the physics. That's why these models are different. Some physics we understand, all of these models capture them equally. Some physics I don't, that's what those models parameterize, and that's the blue part. The orange part is the irreducible uncertainty. That's the intrinsic variability in the climate system, and that's the one that is that extreme sensitivity to initial conditions. Very small changes in initial conditions still give rise to uncertainty.
So 2 points, sir. This is something new for me, so pardon me if I fall short of expectations. Has geodesy been integrated with the study of climate science so far, since you've been following this in depth?
Yeah, go ahead, yes.
That are there any gaming or say simulation models which can be used for at least getting an understanding of the issues involved as well as the impact factor if you try and gain for decision support at a strategic levels?
Very good questions. So by the way, I was very impressed with what you said the other day, yesterday. So I'd love to talk with you offline. But yes, to both. So in terms of geodesy and geomatics overall, where it has been used most, so these models that I'm talking about, these are simulation, physics-based numerical simulation models. Those have been used in the context of impacts, climate change impacts. So for example, if I say, this is what is happening in terms of climate, now what does it mean for a city? What does it mean for infrastructure? So some hydraulic infrastructures may be designed based on of intensity, duration, frequency of rainfall extremes, right? Now, if those change, then what does it mean for the design of infrastructures and at what scale? Similarly for water resources. So for those kind of things, yes, right? So, but these are communities that are used to dealing with not climate per se, but with water, with buildings, with this, that, right? Who are used to dealing with shapefiles, who are used to dealing with ArcGIS, etc., etc. Then they bring in this as an input. So in that sense, yes, they have been used. Your gaming question is very interesting. So there are multiple ways in which this is done. Yes, agent-based models and other kinds of simulations and some game theoretic approaches have been used. Even simulations with real people, right? So war gaming. I was actually part of a war games which was organized by the Center for New American Security. This was towards the end of the George W. Bush era. So what happens is when the Republicans or Democrats come to power, the other party, people of the other party go into hiding in some big Washington DC based think tank. Some of my friends here will know that. So Center for New American Security is a liberal progressive think tank. They knew that next election they are going to most likely come to power. So what they organized is they brought people from the top polluting, greenhouse gas emitting nations or regions, US, Europe, China and India. And I was at the Oak Ridge National Lab, then they called me. So they had this actual simulation, meaning with people, a war game simulation, where they wanted to run this thing as if this is for real, but of course this is not real. And they wanted to see how this thing evolves and what kind of outcomes you might get. It was a fascinating experience. For me, it was lucky that they asked me to join a team, and of course they asked me to join the Indian team, which was great. But I have been so fascinated that each time now when I bring some of my undergraduate students across to study climate change impacts adaptation, I have a simulated war game at the end of each course, which goes very well. But yes, those kind of techniques are being used, has been used in different ways, maybe not as much as they should be, but to some extent, yes. But you had another question?
I'll take them offline.
Okay, okay. Okay.
So before I ask my question, I should submit that I'm not very technically knowledgeable about the subject I'm going to bring up.
Neither am I, so feel free.
Okay. However, I was going through some scientific article a few days back where it was said that with the advent of quantum computing and quantum machine learning on subjects like that, these measurement of the modeling of these climatic things like temperature and all that, the simulations might be more accurate. So could you please throw some light on that?
So I don't have any idea about quantum computing as such, other than my idea gained from Star Trek and what I learned from my brother, who happens to do some things in this area, who actually gave me this viral thing also. But so I don't feel qualified to answer that question, but what I could tell you at some point, maybe this is an offline discussion, is if we could compute much faster than we do right now, what are all the new and fascinating things that we could do, which we just cannot. We feel so limited right now, because we want to see these climate models were built at some point to give broad assessments about atmospheric movements, understanding of the system, things like that. Then from atmosphere we went to land surface, to oceans, to this, and it remained like that. So at very large scales we are okay, but by the time we get to I want to do something for the city, for this water, for this thing, I have to do a lot of hand wavy stuff, right, which can hopefully improve a lot. And even things like convection, right, there is this air mass that heats up and it goes up, and then you have this huge thunder, these huge clouds, and they come down as rain. Even that thing is very hard to actually model because it's so high resolution. So if we could do that kind of thing, I mean, if we could get to these kind of computing advances which can help me do these things much better, these resolutions much better, I mean things better at higher resolution, I could do a lot of wonderful things. One caveat there, of course, is that the physics will have to catch up also, because sometimes what happens is, okay, I think I have so much computing power, I can do all this, but the physics that I have developed is at another scale, and I get what is called GIGO, right, garbage in, garbage out. But I'm sure that problem can be solved. So computing problem is one limitation, at least from that side I can say. As far as quantum computing and so on, I'm not the person.